that's good. Good on that too. Alright, that's good. Okay. Not too bad. We'll just do our first string together. We're going to be doing the 2017 AP Calculus AB free response questions. This will most likely be voted up and saved directly onto the channel. So what we'll be doing here today is that I'll be going through all of the problems. We'll be correcting it ourselves as we go through it. And hopefully we should be able to learn and have all these free response questions recorded. So this will be off to the side. We'll be having all the questions. Hopefully I should be able to put them down properly onto the paper so that all of the actual questions can be read just straight off of the notebook itself. All calculations, I believe, with calculators will just be done online through either Symbolab or Desmos. So we should be able to change screens if we really need to do that. But for now, we'll just go about this. We'll see how well we can gain some more attraction for this kind of thing. So why don't we begin here? I have question number 1 here. We have this table. I'm just going to make it ourselves here. So H will be in feet. And then A will be in hours and square feet. Okay. So let's see here. I have the values of 0, followed by 2, 5, and 10. Okay, 50.3 feet squared, 14.4, 6.5, and 2.9. Very good. All right, so we have here, right now, an actual question here. So they're going to give us a content here. Tank has a height of 10 feet. The area, which is going to be an H, is measured in square feet. So A is continuous and decreases as H increases. And then we have the table. Okay, cool. So they're asking for in part A, let's use a left Riemann sum with 3 subintervals. And then we want to approximate volume. Okay. Hopefully the writing there isn't too bad. I think I can improve that as time goes on. But for now, I think hopefully we should go along with this. So we want to also indicate units of measure. All right, very good. So let's have a look here on what we have. We got our situation right here of the different sizes. So let's go make sure we have, let me see if I can get a different color here. I think I have my green available. Not too bright, but I think it should do. So left Riemann sum, of course, means that we're going to be using the left heights on the table that are provided at the 50.3, the 14.4, 6.5, and 2.9. So hopefully with those we can be able to differentiate exactly the different heights on the left side with 3 subintervals. So we're only going to have to make 3 rectangles about this. So again, if we were to make a quick example here, we have the height of 50.3, then the next height of 14.4, the next height of 6.5, and lastly to 2.9. But with only 3 rectangles, again, we're going to be doing 1 rectangle at each of those heights and lowering. And now with that, we can go and approximate the curve. Hopefully that picture should be able to understand what that looks like for most of our people there. And so with that, let's see if we can then approximate a proper area underneath the curve here. So our area then is going to be 3 subintervals. We have 3 rectangles. The first rectangle is going to have a height. Again, the area in this is going to be height 1 times the width of 1 plus height of 2 times the width of 2, and then height of 3 times the width of 3. And the most simplest way of approximating area underneath our curve here is actually going to be just using the total heights multiplied by each individual length of this type of product. So why don't we go about this through one bit at a time here, and we can just plug in straight from the table that was provided. And so with this, we have a height of 1 that's going to be equal to the 50.3 feet squared that was given to us from the table. Then it's going to be the height 2 is the 14.4 feet from the table. And lastly, a height 3 is 6.5 feet squared. And so those are the heights that the different graphs will give. And so from there, we should be able to put in together some of the actual widths so that we can start taking the areas of each of these guys. So why don't we go ahead and do that? So width of 1, again, it is going to be the actual distance between the 2 different x values of this actual graph here. So it's going to be the 2 minus 0 to make that difference. Our width, secondly, is going to be 5 minus 2. And our third width is going to be the last 2 points, the 10 minus 5. What you might notice here is that once we actually come across this is that we have different widths of the rectangles. So some of the rectangles that we get from this Riemann sum is going to be thicker than others. So for example, even though we have the highest rectangle at the 50.3 mark, the actual width of the rectangle is only 2, given to what we recorded here before. Next up is going to be the actual height of the second rectangle is a bit shorter, but it has a width of 3 and the height of 14.4. And then lastly, we have the shortest rectangle, but it does have the longest width of 5 and the height of only 6.5. So there's actually going to be quite a few things that are going to be happening here, is that these will contribute to different areas based on how wide those actual rectangles are. But in either case though, the math is still going to check out on its own because we're just calculating simple areas with rectangles. So we can go through this one little bit at a time with our area now going and going to have its equation with everything that we plugged in. So it's 50.3, that's feet squared multiplied by the 2 feet in the width. I'm going to write vertically here just to save some space, but it's going to be 14.4 feet squared on the next height times 3 feet, and then lastly 6.5 feet squared multiplied by 5 feet. And so from that, we have quite a few different areas that we can now calculate for. And so we'll see what that will look like once we do all the numbers here. So this section though, part 1, is a calculator allowed. And so for what we're gonna do is that, at least right now, it seems to be fairly simple math, so don't need to pull up a calculator here. But our addition here would be 100.6 feet to the third, so that's feet cubed. So again, we're dealing with a volume now, and so feet cubed is going to be important to keep track of for this type of problem. And they're going to ask about that later. Next up, we have 14.4 times 3. So that's going to be a lovely 43.2 feet cubed. And then lastly, 6.5 is going to be 32.5 feet cubed. So we found the area of each individual rectangle, and so now we will be able to describe what the total volume will look like. So with some very simple addition here only to the first decimal, we'll get 3. Well, let's see if we add that 1 there, so 6. Nothing carried, so it's going to be 176.3 feet cubed. volume, right, of the actual height of the volume of the tank in feet cubed that is measured. This is what they asked for. So let's have a look, at least for this. We have that as the actual recommended volume for that. So that's part 1 complete. They did indicate the units of measure. Let's go to part B on this problem now. So let's see here. It says part B, I'll write this down. So does the approximation in part A overestimate the volume in the tank, and explain the reasoning. Okay, very nice. So we have another question about the actual volume of the tank itself. So there's a couple ways to go about this. One is to simply understand what the graph looks like, or two, we can see if we can transition here to actually going to, I wonder what we can do here. I think for this, no, I mean, the only thing we could do really do it would either be Desmos, or we can just graph it ourselves. So let's actually look at a proper graph. So it would be best if we did see exactly what the graph looked like, so that we can determine whether we're over or under approximating this kind of a graph. So let's see if I can draw that out properly, just to see what area we're trying to figure out underneath. So we have our different widths, so let's go across because we need to get up to 10. 4, 5, 6, 7, 8, 9, 10. That's the 10th point of 10. Then we'll go halfway, so that'll be 5. Oh, 5 should be back there. And then 2 and 0. Okay, so we have each of our widths laid out for our rectangles here. That will be helpful for later on. And then let's see if we can get the actual heights now. So we'll go, I think we should go most likely in 10s here. 1, 2, 3, 4, 5, 6. So we can do some approximations just because we can then understand where we need to be at for this kind of problem. So we 50 at 0, 14.4 at 2, at the point of 5 it's 6.5, and lastly at 10 it's going to be at 2, so very close to the bottom. So we can most likely draw this in a, they say it's a continuous function, so we just kind of have to connect the dots in the best way we can. At least for me, I can imagine a nice curve between all these points like this for this kind of tank. So now let's see if we can swap some colors a little bit, just so we can then see how we actually did this kind of integration through approximation. So left Riemann sum again from our previous line of work is that we use the heights of 50, 14, and 6.5. So those are the heights in which those rectangles extended out from, such that we can get the rectangles like this, all the way to 10. So we can see from the graph itself by shading in and comparing it with the actual curve that we have graphed from the table that they provided, this is indeed an overestimation. At least for this, one way we can understand this is that even without this graph, if we can actually make the following conclusions from what we have a decreasing function for this kind of graph. So again, it's pointing downwards as the y values continue to decrease. But then we'd actually go ahead and realize that with the decreasing function is that with a left Riemann sum, at least for what they're asking for, is that we should be able to understand that with going on the left side of the types of the left side of the types of parts on the graph for the heights, we will be able to understand that this is an overestimation of this type of graph. So that is what we've concluded. At least if you did the graph part, or if you pointed out to each one of the parts of this type of function, you'll be able to hopefully get enough points on this part as well, because you've proven everything that they've asked for. Okay, well, let's flip this over to part C, because I am out of space already on this page. So let's see how part C will go. Alright, so in part C, we're still on problem 1, so let's make note of that. Let's see. And this is the AP Calculus AB 2017 FRQ. Again, for reminders that I'll be going over all of the problems. There should be 6 of them, 4 and 2, if I remember that ratio. 2 with calculator, 4 without. And so with that, we should be able to go through understanding the problem-solving steps for that upcoming exam. And so for this, let's see here. We're going to go on to our next steps here. That it says here, the area in square feet. The height h is given by the function f, and it's given by f of h is equal to 50.3 all over e raised to the 0.2h plus h all in the denominator. So quite a bit of a wacky function if you ask me, but it still should be good enough to work through on this side. So the problem continues though, based on this model. Find the volume of the tank, and then we also must indicate units of measure. Okay, so we got this entire function here, and so now we need to find the actual volume because they're giving us an actual function. So just remember is that our function f of h, again, this is given in feet squared. Again, h is also measured in the height of the tank. And now we will need to find the total volume of this actual tank that we're looking at. So with this, we're gonna have to go and run, if we ran an integral of the f of h, dh, so in respect to h in terms of its actual integral, then we're going to gain back another h into, or in this case, yeah, another dimension into this tank. So that will result in us getting the volume in respect to the height of the tank. That's what we need to do. Again, we're going from feet squared. If we take an integral of something of feet squared, and then in respect to the dimension feet, this will then go to feet cubed in the volume. Not too bad for what we have here. And so thankfully, because, well, we actually just need to go find the actual total volume going from 0 to 10. Right? So that's what the table gave us, is that our f independent variable has the interval from 0 to 10. This will be the limits of integration when we actually put this inside of the integral that we set up. So let's have a look here. If we were to go ahead and take that integral, let me double check here. Yeah. Okay. So with that, let's have a look here. So we're going to run the integral for f, which was, yeah, it's just going to be an area function. And let's run it from 0 to 10. The total amount of height in which the tank will go through. And then from there, we'll be able to run the function. So let's plug that in, 50.3 over e raised to 0.2 h plus h in the denominator, dh. So with this, that looks good enough to put inside of our calculators. So as of right now, I'll be switching the screen over to the computer side of things, just to be able to see what that will look like for us. Let me make sure I get to an integral calculator. Okay. Swap that over. Okay, so let's swap over here. I'll be using this on my computer screen, but it shouldn't be too bad for what we have here. Let's actually change that really fast here to make sure that I can still be seen on this. Down. Just so we can see myself just for a little bit while we go over this. Okay. Our first stream, of course, so we'll bear with me as we get through these last bits here, but I'll be on Symbol Lab here. Let's see if I can blow this screen up just a little bit more so we can see exactly what is happening. So I'm going to be inputting exactly what is inside from the previous bit of line of work that we had. If it can go help me out over here. So that was going to be the 50.3 all over e raised to the 0.2h plus h on the outside using h as a variable. So this shouldn't be too hard to put inside of your calculators when you're actually doing the test. And so with that, we can run this through and have a look here. Let's see how long this thing is going to run for us. Normally it shouldn't be too bad unless I need to bust out my old calculator. Okay. Very interesting. Looks like Symbolab doesn't want to help us. Let's hold off on this for just a second here. I have to bust out my old friend here. Let's see if we try this one instead. And hopefully we can get to something better instead. So, let's see. We have the options here. So, upper bound is going to be 10, lower bound is 0. Okay, now let's actually run. It's 50.3. We have to leave this in terms of, well, we can choose any letter we want. Oh, choose H. There, perfect. Looks like this guy is actually better than Symbolab. So, e raised to the 0.2h. Plus h on the outside, dh. Not so bad. Let's have a look at what this looks like here. Interesting. It didn't give us the actual equation. That's fine. We just need to run through the actual result of the integration. Very good. That's exactly what we want. Just some number that they can get down to. So with that, our calculator spat out 101 point. Let's go 3 decimals 325. And then that is going to be in the feet cubed. Yeah, feet cubed will be the actual volumetric amount that we're shooting for here. Okay, very good. Let's switch back to the desk here. so we get to see exactly what that looks like. Okay, very nice. So we end up with 101.325 feet cubed thanks to the actual calculator spitting us out an answer. All right, so that actually will be the answer to 1C. Of course, if we want to go over that really quickly, is that we were looking at the actual area function. This was given by f. By taking the integral of the area function, you will then be able to figure out the volume from that. Not too bad for something on this part. Let's go to part D. So it says here that water is pumped into the tank when the height is 5 feet. The height is increasing at the rate of 0.26 feet per minute. And then from part C, find the rate at which the volume of water is changing with respect to time when the height is 5 feet. Units of measure. Okay, very nice. We just gotta make sure, hopefully it's still legible enough. Again, it will be an improvement as time goes on. But in any case though, let's have a look at this. So by pumping it in, we have a height at 5 feet. We have a rate from that. So again, they gave us an actual volume, and that's the h, the independent variable of this actual equation. And then they give us the resulting rate. So we want to find the actual rate when the height is exactly 5 feet from that. Okay, so by going with, again, the actual height changing, again, that's h prime of t using the height changing factor there. So let's see here. So in other sense, it's dh over dt, so the height in respect to time. Again, they gave us that 0.26 feet per minute at 5 feet of the height. So that's an important note to add in there to make sure that we're looking at the actual result of the derivative of the height in respect to time. So they're asking for, though, the volume in respect to time. So because of that, that will require us to take the derivative of our volume function instead. So our volume function, thankfully, we already taken it. So our volume function is noticeably the integral of our height function that we gave, the area that they gave us back in part C. And this was all part C. So nothing too foreign for us. But instead of asking for the volume, they want the volume in respect to height over time. So what would that look like, right? So by taking the first derivative of the volume in respect to time, that will mean that we go back to the original function, f of h, but we also need dh over dt because of the chain rule. We are able to, let's see, maybe we should change f of t. Its volume is respect to height. So because of that, the chain rule will have us go and remove one instance of the height into the actual derivative. So let's see here. So with the height being changed into a different type of function here, let's go ahead and plug this in. So our actual area here is that it is going to be, the area function was already the 50.3 over e raised to the 0.2 h plus h, and now we can multiply with dh over dt. Again, at 5 minutes, they gave that already to us at the 0.2 feet per minute. Now, 0.26 feet per minute. Now, does this make any sense at all for what we're doing already? Maybe, maybe not. But nonetheless, though, if we would actually check the units, remember, so f of h, that was giving us just feet squared per this feet squared, because that was part of part C. And if we multiply that by the dh over dt that they gave us in the feet per minute, it looks like our units do flow properly. That is going to be the v of h over dt, in the sense that it's going to be the feet cubed per minute. And not the worst thing to happen, at least for us, because we can then easily see that we're working our way towards making the volume a function part of time. So let's actually go about solving this through and through by plugging everything in here. So it's 50.3 over e raised to the 0.2 times the height function, which is going to be 5 plus a 5 in the denominator, multiplied by 0.26 feet per minute. Okay, now this is something looks like a job which is for our calculator. So I'll swap right back over to that and we'll have a look here. So thankfully, I believe our good old friend Symbolab should be able to work properly for us this time. If we can just, if I should be able to get everything working out here. So let's swap it back to our good old calculator. So it's going to be 5s in places of h. So in that part up there, it's going to be 0.2 times 5. And then h is 5. And then multiply all this by 0.26. Alright, good. A lovely decimal. I'll go into 3 decimal spots for now. It's 1.694. Again, the units of measurement here for the volumetric flow rate is feet cubed per minute. Very good. So let's switch back to the notepad here. There you go. So 1.694, that's the answer that we copied back over from this type of problem. So that will conclude problem number 1. I will go ahead and check back with that at the end. We'll do the second problem of the calculator section, and we'll check both of them together to see just how accurate I was at keeping up with this kind of problem here. So let's see, let me just make sure we have it. Need that up there. Okay, good. We'll come back to that. Alright, we'll flip this over and let's get on with problem number 2. Ah yes, this problem does remind me of what I've worked on before on this exact year. But nonetheless though, let's go with this problem. So we have a grocery store. Its store has 50 pounds of bananas on a table. And then the customers remove bananas at a rate modeled by, and now we have the actual function. It's going to be known as f of t is equal to 10 plus 0.8 t multiplied by sine of t cubed over 100. And then for the interval from 0 t all the way up to 12. Okay, it keeps going though. It says that where f of t is measured in pounds per hour, and then t is the number of hours after the store has opened. So it says those years at the end, after The store has been open for 3 hours. Store employees add bananas this time. If I can spell. At a rate of this time, it's got a different function called g of t is equal to 3 plus 2.4, the natural log of t squared plus 2t, and then we have the interval from 3 all the way up to the end at 12. Alright. So, same thing here. G of t is measured in pounds per hour. Okay. So let's get onwards to part A. That was all amazingly just context for this problem. But let's have a look here. So we have the first 2 hours of the store is open. So let's say, let me count. So how many pounds? Of bananas are removed from the display table during the first 2 hours. The store is open. Okay. So with that, let's have a look here. So it's removed. So remember that's the thing we need to keep in mind here, is that removing the bananas is going to be referring to f of t, that function. Again, we have 2 hours in which that these have been removed from. So we want to know the actual pounds though, not the rate. So now looks like we need to go and do a definite integral. Because remember, this is the pounds, f is known as pounds per hour. If you want to know the total pounds, in the first hour, so that's 0 to 2 hours, at least in terms of the time that has been passed, we're going to need a definite integral to work alongside of this. So, by going from 0 to 2 on that function f of t, respect the time, again, unit-wise, that will give us pounds removed. Going back and taking a step back from rate removed to pounds removed. And so that is going to be used with a definite integral. So let's set this up here. It would integral from 0 to 2. And so with that, the f of t function is listed as 10 plus 0.8 t times the sine of t cubed over 100. So remember that this is an actual definite integral, unfortunately with something that we cannot do by hand. And thankfully this is a calculator section for this type of problem. So let's go and see what that will look like then. So let's go and swap over to our good old friends at the integral calculator, and let's go and make sure we're looking at this in a proper way. Let's swap that over. Okay, so it's going to be the integral of, and then I'm going to swap that to t, because they're nice enough to do that, so the limits are from 0 to 2. So let's go 10 plus the 0.8t multiplied by the sine function of t to the third power over, okay, that looks good, 100. Very nice. Let's close everything off and let's go. Let this guy run. Wow, it actually ends up with a manual integration. Not for us though. We care about that approximation, the area underneath that curve. They even did a wonderful job of doing a graph of it, well, a very interesting looking graph, but they ran the integration from 0 to 2 and it ends up with that 21.359 if I round it to the third place. So I'll take a note on that and we'll switch it back. So 21.359 pounds removed. And let's swap it back. Okay, so with that, we ran the integral on that part right there and threw it into the calculator, and so we ended up with 21.359 pounds removed. That is an important note to have on this problem because we took the integral of the function f, which is again the integral from the rate that was removed from this actual stand here. Okay, very good. So that's part A. Let's move it on to part B. So now they want us to find f prime of 7. Using correct units. Find the meaning of f prime of 7 in the context of the problem. Okay, so another step on this factor here is that we need to find f prime of 7. So what would that look like though? I think for us, even before we go through any sort of problem solving, we want to take a look at what that looks like unit wise for us. So again, what that means is that we're taking the function f of t and we're taking the derivative in respect to time on it. Again, we're adding another portion of time on the denominator, so that's going to be the pounds per hour, also another per hour. So in this case, it will be pounds per hour squared. Okay, unit wise, and that's not really meaning that time is in a square fashion, but at least in the sense that this is going to be the rate at which the rate of bananas removed change. Okay, so again, this is gonna be a rate of change for the rate of change. Pretty nice. And so looks like we have the units down, so why don't we go ahead and actually run the differentiation here. So f prime of t is that we're going to take all of 10 plus 0.8 t multiply the sine of t to the third power over 100, all of that with its derivative. Not terrible. And so this actually could be done by hand, so why don't we just go ahead and do that. So the generic f prime of t function is going to be using good old product rule for this kind of guy here. It's going to be 0.8 of sine of t cubed over 100. And then we add that with the other side being the 0.8 t times the cosine of t cubed over 100. And then we're going to need a good old chain rule coming down with another form of exponent rule, which would be 3t squared over 100 for the derivative inside of that. Okay, not too bad, a little bit cluttered, but nothing we can't handle. So from here, we just need to plug in that f prime of 7 as they requested, and we should be able to be well on our way. So working on the next line here, 0.8 sine of 7 to the third power over 100 plus 0.8 times 7 cosine of 7 to the third power over 100, and then multiply by 3 7 squared over 100. Okay, so that is what is going to be going inside of our calculators, such that we can find all this together, and then from that we should be able to then incur what the actual result is going to be. So let me run this through Symbolab, and we should be well on our way. Let's swap the screens here. So let's go with 0.8 times the sine of third all over 100, all over 100. 2.8 times 7 cosine of 3 times 7 squared. All this over 100 again. Okay. Let's see if this will work. And yes, it does. So that ends up all taking out 120 if we run the approximation to the third decimal place, and then this is going to be in pounds squared per, not pounds, but pounds per hour squared. Let's swap it back, and let's also make sure I swap to here. Okay. All right. And so with that, we end up with an actual answer that our calculator spat out to us. Not bad at all for what I have to say about this. So let's make sure that we are on the right track about this. Okay, so let's clean that up. Actually, it doesn't look the best here. So unit-wise is pounds per hour squared. So are we allowed to have a negative in that answer? The answer, of course, is going to be yes. Having a negative there is not a problem. Why? Because that is going to be 8.120 in pounds per hour rate change. Again, and a negative there makes no difference for us. That is going to be just a decrease in that rate for us to be removing. And not the end of the world, but at least will be something good for us to hold on to. So that will be then the answer for part B. And we're understanding that the rate at which they're removing those bananas are changed. Okay. Let's go next here. So they say is now part C. If we can see that, I'm going to push this up a little bit. There you go. Is the number of pounds of bananas on the display table increasing or decreasing at times equal to 5? Give a reason. Okay. So times equal to 5, I believe there's a little bit of a trap for many of the actual people who take this test, is because they might think, oh, time equals 5, well, we have already one of the rates already, we have the f of 5, and then we can go figure out what that is, and we'll be good enough there. But they've kind of forgotten already that g of 5 is also a proper value, because again, t is greater than 3. It's after the third hour is when they start adding more bananas onto the display table. So in this case, the actual work here is that we have a g of t, and now with this, again, f is actually measured in a positive value here, so we need to subtract it by f of t. In our case, of course, is that the time is equal to 5. So we have two rates we need to compare. One is going to be a positive value, one will be subtracted from the other. And so with that, those rates can be compared to, and we can figure out what that will look like for this problem here. And so let's see here. So g of 5 is equal to 3 plus 2.4 times a natural log of 5 squared plus 2 times 5. And we subtract it with the all of 10 plus the 0.85 for t, multiply sine of 5 cubed over 100, all inside of that. Okay, so we have the g of 5 listed as that, this is f of 5 listed as that, so then we can run that comparison, comparing between how much are removed and how much are gained. So we got to go back to our calculator again, going back to our good friends at Symbolab, and we'll have a look here. So it's going to be 3 plus the 2.4 times the natural log of 5 squared plus 2 times 5. All of, subtracted by all of 10 plus 0.8 times 0.5 times of the sine of 5 to the third power over 100. Okay. Pretty alright. So with that, we end up with the solution of 1.153. Again, this is going to be pounds per hour added to the table. So let's swap back for what it will look like for us here. It's 1.153 pounds per hour added into the table for this kind of problem. Again, in that case, G had a larger function value rather than F, so these employees are putting more bananas on the table than the amount that are taken away by the customers. Very nice. Okay. That will be B part C. So, and then I think we should have enough space here, at least for part D at the very end here. Fit this on the one page. So the pounds of bananas at time is equal to 8. So an actual amount that is on the table. That's going to be quite something. So we have to run a couple of integrations here. So we have, if you remember, we have 50 pounds. If you remember at the start of the problem, we can pull up to that, right? Again, the 50 pounds are at the start of the table when the store opens, and then customers start yoinking those bananas. So let's get this started through. The 50 pounds of these bananas are started with, and then we will move to subtracting the amount that the customers take, and they take it for the entirety of the 8 hours, so 0 to 8 hours for the function f of t dt. Again, the number of bananas is going to be in a positive value, at least for this. And then lastly, we need to add in for the g of t. Again, we have to add in for the amount of bananas that the employees are putting back onto the table. Now, of course, the big issue here is that we need to have the correct time frame for g of t, because they don't start adding bananas right on the first hour of the actual table. They will start doing it on the 3rd hour onwards to the 8th hour. So make sure those limits are going to be proper. 0 to 8 for the f, and then 3 to 8 for the g of t. Now this is something that we're going to have to start filling in for. So from here we have 50 subtracted by the integral from 0 to 8 for f of t, which is the 10 plus 0.8t multiplied by sine of t cubed over 100 dt. And we need to add that with the 3 to 8 function of g of t, which is the 10 plus, not 10, sorry. Let's swap that out. It's the 3 plus 2.4 natural log of t squared plus 2t dt. So that might be cut off there a little bit. So we have all of this here as the proposed operation that is happening inside of our calculator. So with that, we need to go once more back to our good old friends at the integral calculator, and we should be going along with that. But I think, let's see, I wonder if we can try to go with Symbolab, because this guy is going to have to be done in parts by the integral calculator. So let's swap it back. Let's see if our people at Symbolab can help us out here, because we're only going from 0 to 8 for f of t, which is the 10 plus all of 0.8 times t. That's 0.8 times t, and then all of that's still also multiplied by sine of 3t to the 3rd power over 100. Oh, make sure we put that in properly. All of this is dt, and then we need to add that with another integral This time going from 3 to 8 of the 3 plus 2.4 times the natural log of t to the third power, or second power for this, plus 2t, all that dt. Okay. So it's just a one-for-one copy of all the things that we put into our paper. So let's have a look here. If Symbolab can get us what we want here. I really do hope so, because I'd rather not go and try to integrate every little part on our other integral calculator. But we'll see. Yeah. I don't know. Well, for whatever reason, Symbolab doesn't really want to help us out here. Okay. I can't do multiple integrals with this guy. So we have to do this one step at a time here. Just bear with me as we get across with this, and it's all in t. So 0.8 times t times sine of t cubed over 100. Okay, this is going from 0 to 8. That looks good. Let's run this through. So I'll make these notes here. We'll take a look once we get through with this. But 77.879 is that approximation, and then let me approximate for integral g. Remember, that starts at 3, not at 0. And then we'll go with 3 plus 2.4 times the natural log of t squared plus 2t, all in dt. Very good. That matches what we have for our function g. And then we have the approximation of 50.9.64 of what they've added back. 964. Good. Okay. So now we can go to Symbolab here, and I can just throw in everything together. So let's go 50 minus 77.879 plus 58.964. That results us with 31.085 pounds remaining. Alright, let's swap it back to our desk camera so we can have a look here. So with this is that we ended up with that result here. So we got 31.085. Remember that I had to go, in this case, hopefully shouldn't be with graphing calculators, I had to run two separate integrals to end up with two separate values that we'd have to add up later. That's 50 minus the 77, and then adding the 58 back, thanks to the employees adding those bananas back. And that will conclude part D. Very nice. So those are the first two questions done on the calculator section of this problem. What I'm going to go do is that I'm going to go now and swap things over back to our first set of problems here. And with that, I will be able to go and correct all the things that we went over. Hopefully, with me being able to have a bit more experience on doing these types of problems, I like to believe I get 100% on this. But anyways though, let's have a look here. So the volume that ended up here in problem 1a, the 176.3 feet cubed in volume, is that one, this is correct. So I'll make a note for that myself. That's good. And then the 2 points, one is that they're doing the left Riemann sum. So this is the one that actually contributes to my points on this problem. So we did do a proper left Riemann sum. And then of course 2 is approximation, which is going to be the actual answer itself. So looks like 2 for 2 on part 1a. That's nice. Okay. And then it says here in part B that the approximation in part A is an overestimate because a left Riemann sum is used and A is decreasing. That's exactly what I said. So decreasing function and using a left Riemann sum, that is both correct for us to then approve that is an overestimation on that sum. So at least on what I have noted here, we're pretty good on part 1A and B. We're 2 for 2. Not bad. Let's swap it over to part 1C on this side now. Part 1C gives us a 101.325. That's exactly correct. So it looks like we're good for that. And then it says here, at least for we need the integral, and then secondly, we need the answer. So of course, answer is good. And then the integral we did have set up exactly here before we threw it into the calculator. So that is both parts of this problem that are solved for and are good to go. Okay. And then next up, part 1D, going further down, 1.694 cubic feet per minute. That is the correct answer. Very good. And then with that, we need to, again, they wanted us to show that we have dv over dh multiplied by dv over dt. So it's a little bit scuffed over here for what I have, but that's this step that I mentioned right there, is that with chain rule is that we're going to have to go and take that derivative, and so it's going to give us the original f of h function and the dh of dt, which was provided to us at the start of the problem. So with both of those locked down, again, that showed us how we got dv over dt at the end of this. So this is also going to be, again, I also wrote that down over here as well, is that this is indeed the next part, the correct derivation for us to result in the actual correct answer. So looks like I got full points on problem 1. Not too bad. Let's go over to problem number 2 then. So looking down here is that I have the actual integral here going out problem 2a. Let's see, 20.05. Interesting. So it looks like this one's a little bit off. We might need to come back to that one. Okay. Its first 2 hours. I might need to go and take a closer look into that. But the integral, I believe, is still correct here. And 10 plus the 2 cubed. Everything else seems fine. I wonder if this is a thing between degrees and radians, but I highly doubt it though. So the integral is good though. So it looks like we're 1 for 2. Again, I'll take a closer look on that. But that is good reason for us to take closer looks at our problems. Okay, next though, the -1, part 1b, -1.82. Yep, that is exactly what we wanted, so this is correct on that answer. And then the value and the meaning. So yes, so the rate at which it's decreasing, yeah, the rate itself is decreasing. Again, that's the rate change. That is also going to be the good meaning behind the value. Okay, 2 for 2 on part 2b. Then going for part C. So we're going to have the actual g of 5 minus f of 5. They want us to consider both of that. So again, what I have written down here as to both doing g of 5 and then g subtracted by t to figure out what the new rate of bananas are is important. And then here we get a. Did I subtract that properly? Because unfortunately the answer is incorrect. Very interesting. Okay. I think we'll have to see if there's something going off with that. So it's this is incorrect. We have a different value. I'll just take a note of that and see if I can refer to that. 2.263. Okay, but the answer is still good, and the reason, again, yeah, the reason is still fine, at least for us. So 1 for 2 on that one as well. Okay, and then lastly, part D here is 23.47. Very interesting. I did exactly the way that they set up here. I wonder what the main issue is on this. So the integrals, so that's actually 2 out of 3. The integrals are exactly what they've set up here. So the 50 pounds that we started with, the 3 to 8 integral for g of t, and then 0 to 8 f of t. Again, this is exactly with the right sign, subtracting and adding. That's exactly what the test wanted us to do. But it looks like there's something a bit off with our answer. That's 2 to 3 there. So a number of things to try to reconcile here in question number 2. So let's have a closer look, shall we? So going back at question number 2, hey, that answer is correct. I wonder if let me try to see here, because the integral was set up exactly the way that we were supposed to with let me zoom in here for you. So with that integral going from 0 to 2 for the function f of t, it's just the integral of t, we're not adding anything to it. We'll see what that looks like. So let me go back to this guy here. So we want to go from 0 to 2 on the f of t function. F of t, again, I'm going to copy it 1 for 1, is plus 10 plus 0.8 times the sine all of t to the third power over 100. And that is exactly what f of t looks like. That's looks like I did a calculation error, because that is exactly what we're supposed to be getting. So that is an oof by me. 701 pounds removed off of this guy. Okay, so this one looks like it's going to be on me, and the actual setup is exactly what I wanted to do previously. Just looks like I might have inputted something incorrectly or didn't check things through. So that is part 1A dusted off for. Then let's go next to 1C. 1C needs to have a closer look at it. So 1C, I set up exactly correct too, g of 5 minus f of 5, but we end up with a completely different answer. So let me have a look here at Symbolab. I want to make sure I'm doing this properly. So it's just, there's no integrals here, it's just simple subtraction of two different functions here. So it's g minus f. I wonder if I did that incorrectly. So 3 plus 2.4 natural log of t, in this case is going to be 5. Maybe we should go and put these inside of the right parentheses just so we're clear on what we want. And then it's 5 squared plus 2 times 5. Okay. So that is the function of g. Now we subtract it with the function of f, so it's all of 10 plus, if I can make sure I'm typing properly, 0.8 times t of 5, and then all that multiplied again by the sine of 5 to the third power and all of u over 100. Okay. That is the way that it looks like. Negative 2.26. Okay. I don't know what is happening for me to end up with these odd answers, because my setup is correct. It just looks like I'm doing the wrong type of thing. So 2.263, that's correct. C is dusted off. I think this is kind of important too for a lot of students now learning from this, is that our calculator answers must reflect properly. We do need to make sure that we're inputting everything to the calculator properly. Again, these types of mistakes, although thankfully they'll give you partial credit on the exam for setting up the proper problem, of course we don't want to be losing any points by simply doing the wrong type of execution, and that would not be good at all. Okay. Lastly, let's go to part D here. This is the main one here. I want to double check our actuals, because this is already our f function that we've already tried it true properly. So let me have a look here. Is there something that doesn't match here? 81.46. That looks like I put that incorrectly into this guy the first time. So yes. So 81.46.461 off, that'll be the function of f. And then we need the function of g done properly now. I'm going to run that again. So g is noted as 3 plus 2.4. Let's see, maybe order of operations might be an issue here. 2 more times the natural log of t squared plus 2t. And again, this needs to go from 3 to 8, not 0 to 8. Let's have a look here. So redoing function g on that problem, 50.964, that's still good. And so with that, let's see that because one value did change, it's going to be 50 instead minus 81.461, adding in the 50.964. 27.503. Let's see here. 27.5, 27 is 23. Oh, what is happening? 5964 and 3 plus 2 times the natural log 2.4 natural log t squared plus 2t, and that's it. And going from 8 to 3. Or 3 to 8. Starting at 3 hours, which is exactly what they wanted here, starting at 3 hours to 8 hours for GFT. Okay, is there something off with my... Let's do this again here. So give us the value of t going from 0 to 8. So this is going to be f of t, which is 10 plus 0.8 times t times the sine of t to the third power over 100. There's upper lower. Okay, I mean that doesn't really matter here. I'm just gonna swap the sign for us. Yes, it 70. What? But that is what I started out with. Very odd. Because my current answer with 31 is too big. I'm going from... oh, what? No, that's G. That's correct. Yeah, 3 to 8 is correct for G. And then... F. T to the third over 100, yeah. And so... Did that remove... Oh, that removed it all. Oh, whoopsie. Okay. Let's reset that. Upper is 8, lower is 0. 10 plus the 0.8 times sine of t to the third over 100. Okay. We don't have enough here. 58964, and that's G that needs to be added, and 77.87. Too small for what we need here. This is the same thing here, so 77.879. And we intentionally made sure that G is only going from 8 to 3. That we've already That's a bit odd. I can't seem to match. I mean, yeah, I have it set up exactly the way it's supposed to. Well, we can try another time once I finally get my graphing calculator, and I think from there we should be good enough to move forward. So why don't we go for, let's see, okay, there we go. I can get some chat responses here. Yep, so we'll be ending within hopefully another bit less than 2 hours here. But so far, looks like we got everything else sorted out. Setups looks good, so it'll be onwards to some non-calculator problems. Hopefully that shouldn't provide too much of an issue for us this time. Okay, let's flip it over now. We'll go 2 at a time. This should be a little bit faster, but still we'll go 2 problems at a time, so I have 2 sections, 4 problems here. So let's go with problem number 3. Inside of this guy here. Let's make sure I get this all squared away. Make sure we're straightened out for the camera. There we go. Okay, let's go onwards to problem number 3. So we have a graph here. Let's see how well I can graph. Let's go here. It goes to -6. Not too much on the vertical. So let's see, we go 1, 2, 3, 4, 5, 6, 5. Okay. And our height really only goes up to like 2. So we can go double on that. And then we can go double on this. Okay. Good. -6, 2. We're going to start plotting some points here. -2, 0. 0, -2, 2, 0, and then 3, 2. Okay, so let's see how well I can manage to graph this. So we do that. I suppose because it's a little bit elongated. Do something like this, something like this, and then on the 1, 2, 3, 4, 5 mark. Like that. Okay. Not so bad. Okay. So we have our graph looking like this. And so they'll give us some more notes here. So the function f is differentiable on the closed interval, never 6 to 5, and satisfies f of -2 is equal to 7. And look at this graph. This is already a graph of f prime, so this f prime of x. That's something that we should note and remember to keep in mind for this problem. So the graph f prime of x is a semicircle in 3 line segments. So this is a semicircle. Just as a little reminder that we can use simple area functions to determine the area of this graph. And then we have that figure right there. Okay. So now we want to go find the values of f of -6 and f of +5. Alright, so how will we go about this? Is that we're going to need to understand, right, that we have the graph f prime of x, and now we need to go figure out what the original function is. Because they want original function values just f, not f prime for this set here. So in order for us to find f of x, that will be the integral, indefinite integral that is, of the f prime of x dx. We're going to go take a step back on this type of function. Of course, how are we going to do that? Well, that's going to require us to go and run, for us here at least, is that it looks like we need to go and use fundamental theorem of calculus, at least for us. And so with this, we will be able to determine that for the, so it's all differentiable from -6 to +5. Yep. And so with that, we're gonna have to go and do some parts here. So f of -6 is going to be a part of the definite integral instead, right? Because we do have a point here, that f of -2, 7. So if we use -6 going from -2 to -6, Again, that itself is going to be the result of a definite integral. In our case though, -6 is the lower value, so we actually need to swap this around instead to f of -2 minus f of -6. And at least this can match up the -6 that they asked for at the start of the problem. That means that if you run the definite integral from -2 to -6 for the derivative function, that is how you can get the value of f of -2 minus f of -6, and we can solve for that accordingly. Okay, so this actual integral, again, that's going to be an area problem for us. We need to get the area from -2 all the way to -6. And that, of course, with that being -2, is going to be this entire section here of that triangle. Not too bad. That's just simply a triangle going from the peak all the way down to the x-axis. So the area from, I can make the note here, from -2 to -6 is simply a right triangle, which would be 1/2 the base times height. So going from -2 to -6, that's a base of, again, -2 minus -6. And then the height now, from -6, it will go all the way up to +2 on the graph. Okay, and then from there, we can go run the simple multiplication with a nice half canceling with the 2. That'll be a +4 as the area. Okay, so again, that is the area for the actual definite integral. And we do have f of -2 already laid out for us. So it's 7 minus f of -6. The point is going to be giving us a total area of 4, thanks to the fundamental theorem of calculus. So we just need to move some things around, adding f of -6, subtracting 4s. So f of -6 is equal to a +3. That is the first part of the problem. Now we need to get to the second part. So f of +5 now is going to be using another definite integral, this time starting at the -2 that was given, going up to 5. And using the fundamental theorem of calculus of that derivative, we end up with that equation. So same idea here is that we need to find the area of this, and then we have the point already given at f of -2 of +7. So we're going to need to find the area going from -2 to +5 as stated right there. From -2 all the way up to +5, we have a couple things going on here. We have a triangle, and we have that semicircle, but the semicircle is underneath the axis of this graph, meaning that we're actually going to have an area of a negative value when we add it up with that triangle. So a semicircle, of course, is going to be pi over 2, pi over 2, not 4, pi over 2 times r squared, right, for that. And then the triangle means that we're going to have to add in instead. So this is going to be negative. With the triangle, we're going to be adding in a value. The value of course, the base being 1/2 times the base of 3 times the height of 2. That all can be determined by actually looking at the graph in a little bit more detail. So the radius, though, for this circle is going to be a +2. It goes 2 out in either direction. So let's go and run this. So it's going to be 2 squared plus 1/2 and then times the 3, simplifying that. So this case is going to be -2 pi plus 3. Because this is a no calculator section, this is as far as we can really get for the area. So remember, we just did this to solve for the area underneath that graph. So now we need to do some last bits of algebra here, such that f of 5 can be isolated here. So we'll add the +7. So f of 5 is equal to -2 pi plus 10. So that's the second part. So if you want to box everything here, f of +5 is equal to -2 pi plus 10. This will be the solution set that we get for the 2 parts that were asked for in this question. Very good. That's part A. Isn't that great? Let's go to part B. Somewhat interval is the graph f increasing? Alright, and we need to justify that answer. Well, this one is not too bad. If we just want to look at an increasing section here, again, this is already the graph of f prime of x, and we want to know the original function f and how that is increasing. So, going back to the graph though, is that means it's going to be everything that is above the x-axis. Again, positive f prime of x values, if I make a note here, right? So, if f prime of x is greater than 0, then the original f of x graph is increasing. Not bad at all for what we're doing with here. So with that, we can have the actual intervals. Again, this is going to be from -6 to -2 that we listed here, and then +2 to +5 listed out there. So let's see if we can make all that match. So that's going to be -6 to a -2, and in a union with 2 to 5. That would be the overall x intervals in which the function f is increasing. That was pretty short for a part. Next, part C says here, find the absolute minimum of the value f on the closed interval -6 to +5, and we justify that. So we have some theorems here that might be helpful for those who remember that we have the intermediate value theorem, meaning that extreme value theorem, that is, where we can understand where the maximums in terms of the absolute sense, so the highest that it can go, is usually going to be turned with. So of course we have any sort of local maximums here for this function, and local maximum for the original function off of the first derivative graph means that we need to go from a positive to negative crossing, which would be right here, right at x equals -2. That is a local maximum. We can look at the actual value of it at a later time, but that's one good note to have. And other local maximums can be determined by either the endpoints of the graphs. So other candidates that we can look for is x is equal to -6, and then the x equal to +5. Those will be our candidates for possible maximums that we can look for. Obviously, the largest one amongst them will be the absolute maximum, thanks to what we can decipher from that. So let's have a look here. So x is equal to -6, x is equal to -2, and x is equal to +5. But well, what do you know? -6 and +5 were already determined in part A for us. So that's pretty nice. And then the x is equal to -2. Unfortunately, I'm smearing ink already on my papers. So x to -2, that was already given to us as well at the start of the problem. So we can go ahead and run some comparisons here. Okay, -6 came from our previous problem. That was a +3. -2 is given to us at the beginning of the problem at +7. So we can write that down for comparison. And lastly, 5 is -2 pi plus a whole 10. Now, of course, even though this is not an exact number, the f of 5, we can run a quick approximation that if -2 of 3.14, a fair approximation for pi, is added with 10 with it, and that's be -6.28 added with 10, giving us a +3.72. So if any of them were to be the actual absolute maximum amongst these three possible candidates, it would be the f of -2 right here. That would be the only eligible one to be, if we know here, is going to be the absolute maximum. Pretty good. Okay. Well, let's see if we can shove in this last part D, in this problem, and we should be able to figure this out. And I'll be concluding this problem here. So part D. So for each, we want f double prime of -5 and f double prime of +3. And do they exist is the real root of the problem here. Okay, so at those values, f double prime negative 5, f double prime of 3, let's have a look. F double prime of negative 5 is going to be right here. So that's a point on this actual line for the first derivative graph. So there definitely is a way to find the second derivative. So let's make a note on that. F double prime negative 5, again, that's a check. We can find that. That's pretty good. But f double prime of positive 3 is going to be right here on the peak of that triangle. F double prime of 3. Now, what you might notice here is that we are going in two different directions right at that point, which means for us, this is a no-go, so cannot find on this guy. Okay, and we'll get to exactly why in just a second. But with f double prime of positive 5, we can definitely find that. It's on a simple line. Again, if you want to find the second derivative, we want to take the derivative of the first derivative. That will up us to the second derivative. We just need to do some very easy slope line equations here with finding the slope of this. So the that point there was negative 2, 0. So let's see. So y2 minus y1, which was a positive 6, positive 2. And then x2 being a negative 2 minus x1 negative 6. So that's negative 2 over positive 4 is equal to a negative 1/2 slope. So this already is f double prime of 5. We can find that. It's pretty simple. But we're going to make the note that f double prime of 3 does not exist, because f first prime of 3 is a corner. Oh yes, a corner. We have that note to make because corners are going to be a big factor as to whether or not a function is differentiable at that point. What do we mean? Is that, again, at f double prime of 3, if we were to take a second derivative on this guy, right, derivative one more after what the graph already gave us, well, at a corner, do we actually know the direction in which this guy is going? Answer, of course, is going to be no. We don't know the actual exact slope at that point, because we can either be increasing at the point before the slope or decreasing the point after that corner. So because it is unsure, and that because it's going basically both at the same time, we will be deciding that we cannot find the derivative for that point on the function. So because of that, we have both sections of the answers, and that will conclude problem number 3 for us. Pretty good. We'll hold on to this, and I'll complete problem number 4 before we go back to check. Let's flip this guy over, and let's go ahead and recenter right there. Okay, let's make sure that we're all good to go on that. Okay, so let's flip this over, my packet here on the next part of the problem here, problem number 4. So at time t is equal to 0, a boiled potato, wow, very relative here, okay, is left to cool. So the internal temperature is 91 degrees C at time is equal to 0, and then the internal temperature is greater than 27 degrees C at all times t is greater than 0. Okay, so we have the differential function dh over dt is equal to negative 1/4 of h minus 27, and where h is in degrees Celsius, and h of 0 is equal to 91. Okay, we have, looks like, all of the stuff that is simplified over here in our terms. So let's have a look here. Let's start with problem A. So write an equation of line tangent to the graph of h at t equals 0. Use this equation to approximate the temperature timing. Okay, so equation of line tangent to h at t is equal to 0. Use equation to approximate internal temp at t is equal to 3. Okay, so we actually have a two-part problem here for this guy that we need to go and discuss here, is that we need to find the equation of line tangent to h at a specific point, and then we need to do an approximation from that line at a different point. So line tangent to equations, of course, means that we have to do the first derivative. Thankfully, they already gave that to us. dh over dt is already that slope of the line itself. And in this case, if you want to make that note here, that is the slope of the line that we're dealing with. Okay, and so with that, we can go and take a look here. Let me make sure I get this set up. Okay. All right. So with that slope, again, we're going to do at t is equal to 0. Okay. So the thing is, though, that this slope is not in reference to time right now. This is measured in the heat itself. So they already gave us the time equals 0, the h is equal to 91. So we can go and plug that in. So our actual slope of the line for this guy is negative 1/4. 91, 27, 60 is this 64. So it's negative 16 is the slope of the line. So again, our simple line equation is y is equal to mx plus b. We ended up with a slope of negative 16x plus b. Now we don't know that intercept. And so that will be pretty simple because our intercept already is given at the point here, 0, 91, thanks to the problem earlier. And so with that, we can go ahead and do the 91 as the y, negative 16, 0 plus b. With some simple solutions here, b is equal to a positive 91. So in essence though, our actual line, 16x plus 91, is going to be the equation. Now we can also make it in terms that they want for us in the problem. So the h, which is the dependent variable, 16t is a independent variable. So we can get that set up here. That's the first part complete. And now they want to change it to time of 3 instead. So h at time of 3, we plug that in there, is negative 48 plus 91. So h at the time of 3 instead is going to be either 43. Again, that's degrees Celsius for the actual heat at a specific time. All right, pretty nice. We got both parts of part A done. Let's have a look at part B. So we then have to use, we want to find the second derivative, d squared h dt squared, to determine if part A is over or underestimate. Okay, and then that's again at the t equals 3 point. Okay, very interesting. Okay, so the way that we think about this, right, is that we have some sort of, so we already decided, right, that the slope at t is equal to 3, and the dh over dt, what that gave us though was a negative 16. So that is a decreasing line here. I'll do it in a dotted line down there. So how do we know that we're over or underestimating where the second point is, right? So let's say, for example, we take one arbitrary point right here, that's t is equal to 3. T was 0, sorry, that's where we started with, that's the tangent to graph. But then we have extrapolated this to be reaching down somewhere down here as t is equal to 3, right? Because we were doing a tangent line graph, it just touches it at one point and it's a straight line after the fact. But now we must determine, are we going over or underestimating, and how can we use to go along with that? Well, with this being the second derivative for this, I should use my green pen. I'm correcting with the red. So with that, with the second derivative again, this is going to determine concavity. Right? So how is the actual second derivative going to help us with understanding if we're going over or under? Well, quite simply, again, depending how that curl goes with concavity, and concave up or down, and that'll determine if we're going to go something like along the lines of this. Right? Concave down would usually help us understand that we are going with an overestimate because the graph will curl downwards, or a concave up, right? And we are still decreasing with the concave up. So concave up, graph will look something like this. In that case, that will be an overestimate. That'll be an underestimate because we'll be underneath the curl to the t is equal to 3. So maybe the conclusion here again. So concave up is going to be an underestimate, and a concave down is equal to an overestimate. Again, both these are in reference to the second derivative of dh respect to dt, and where that is going to lead us based off the sign of that result. Very good. So now it's time to actually get to the business about where that second derivative is going to go. So the first derivative already is noted as this. Okay, so let's get to the second derivative respect to time. So everything else really is just a coefficient, so it's negative 1 over 4 dh over dt minus 0, because that constant will go to 0 in another derivative. And so now we need to substitute back in the dh over dt. There's negative 1/4 with another negative 1/4 h minus 27. Not so bad. Not so bad at all for us. So let's run through this guy again. So it'll be positive 1 over 16, and then it'll be h minus 827. Okay, but the concavity now again is going to be, so this is going to be the second derivative respect to time. Again, at the height of, in our sense, 43. Okay. Well, we don't need to do 14. No, our height is going to be 91 because it's at t is equal to 0. We need to know the concavity exactly at the starting point in time. So and that is 1 over 16 times 91 minus 27. So that's 64 over 16, we made positive 4. So this is a concave up system at time is equal to 0. I can write that down properly. Concave up at time is equal to 0, meaning that we're concaving up and away from the line. So that means that we will be an underestimate. And so I'll rewrite that. Concave up at t equals 0, such that with that result we have both the reasoning and the result of our estimation there. All right. Part C says here that for t is greater than 10, we have an alternate model. So d of g over dt is equal to negative g minus 27 to the 2/3 power. And then g of t is in degrees Celsius, of course. And g of 0, same point here, is 91. Okay. So, based off of this, what is the temperature at t is equal to 3? Good. So now they give us another equation that we need to go and solve for. So this is a good old separation of variables here. T is is equal to negative g minus 27 to the 2/3 power. Okay. So with that, we can go ahead and now solve for this in respect to time. We gotta do some variable splits, but I think with that will be all the good for it. It's 2/3 on 23. Okay, so we'll go and swap some things underneath. We'll swap the way that the variables of integration is going through. And so that way we can run through this integration. So we can now from here integrate on both sides. Okay. And so with this we get the g minus 27. Now this needs to be at the 1/3 power. So that thanks to power rule, that will give us the 2/3 going into the denominator after the derivative is taken. But that also means that we need a -3 multiplied on the outside to cancel out with that coefficient. And then we just get t on the other side. And of course the plus c. Okay. So we can now move everything over to make it a g as a function of time instead to make our lives easier. So g minus 27 to the 1/3 power is equal to t over -3 plus c on that side. And then we can go t over -3 all that cubed plus 27 plus c. All right, not bad. So remember at t is equal to 0, g is equal to 91. So 91 must be equal to 0 plus 27 plus c. C must be equal to 64. So in that case, it's good. G of t, the new function, is equal to t over -3 to 3rd power plus 91. Well, now everything matches from the way that we took that integral. Not bad. So from there, we can take g of 3, plug everything in. So it's 3 over -3 to 3rd power plus 91. And we might be running into a little bit of an issue here. Let's see here. Let me double check on some of this. about 2/3 of the denominator. I'm trying to think here because it maybe seems like g should be the function of t. So let's try that again, because this is not really working out. Looks like I might have jumped the gun on this. So let's restart again from what we started with here. That dg over dt is equal to negative g minus 27 of 2/3. Again, given that g is a function of time, we can go negative g minus 27 2/3 dt, and we integrate that instead. So our g of t, our new function, is going to be negative g minus 27 raised to the 5/3 power plus c. And then with that, we're just going to need a positive 3/5 to cancel out with that coefficient. Okay. So with this, g of 0 is equal to 91. And then that'll be 64 in there plus c. So 5/3, that means taking out 3 of them means it's a 4 raised to the 5th power. 4 raised to the 5th is going to be, that's pretty big, huh? 64 times 16. That doesn't make much sense either. Wow. Alright. I think on this one, I might need to reconsult back with the resulting answer because we're having a little bit of an issue here. I think, is my first answer really the correct way of doing this? Yes, it was. And then okay, I see how that works. Okay, let's try that again. A little bit of a hiccup on my side, but all should be fine so long as we improve on what we're doing here. So let's do 4c again. So we have dg over dt is equal to negative g 27. Okay. And then we have the initial point g of 0 is equal to 91. Okay. So let's go again through the first step that we have here. I was on the right track here. I was just second guessing myself. It's 2/3. Okay. This is equal to the negative g minus 27 to the 1/3 power, and we need a 3 there to cancel out with that, is equal to t plus c. So the idea being here that because we have this point already here, we're going to use that immediately if the camera can focus. Focus on that. Okay. Good. Alright. Okay, let's make sure that we can actually see what we're writing on the screen. So now we can implement that so that we can find out what the value of that c is and move everything over accordingly afterwards. So negative 3 of the 91 minus 27 is equal to the time of 0 plus c. So from this will be negative 3, 64 to the 1/3 is equal to c. C must be equal to negative 3 times a 4, which is a negative 12. Good. So restarting again to now isolate g as a function. So it's equal to t minus 12. And g minus 27 to the 1/3 is equal to t minus 12 over a negative 3. And then now we can go and take the cube exponent on that. And so lastly, g of t is equal to t minus 12 over negative 3 to 3rd power plus 27. Now from here we can finally go and understand what g of 3 is. 3 minus 12 over 3 negative 3 cubed plus 27, which is equal to negative 9 over negative 3 3rd power plus 27, which is equal to a positive 27 plus another 27, which is equal to a positive 54. I wonder if my negatives were the main issue out there, because everything else seemed to be good. It's just that my negatives on my previous... Yeah. I think there was something going on with the negatives here, because It should have gone the other way. Okay. In any sense, though, we've got our answer. And of course, I'm pretty sure the answer sheet would have called it for 12 minus t over positive 3 to make sure people would less likely be messed up here. But very good. Looks like we have all that we need for us to go and check our answers here. So let's go back to problem number 3 and let's go over every last bit to see what we can improve on. So going here at problem number 3, we now have this is back with our graph here. So it says here that the two parts here was that f of negative 6 is equal to 3 and the negative 2 pi plus 10 on the f of 5. That is good. So that's 1 point each correct on that. And then we need to use the initial conditions. Again, that means we have to set up for both integrals, that and this. So those are all good. So we're all good on part A. Okay. And then on part B, we have the intervals negative 6 to negative 2, and then 2 to 5. Okay. Now, let's see. Increasing on yeah. So they want us to use brackets here. Let me double check on that. Okay. Let me see how these brackets on that. I personally wouldn't, because it's not really continuous there, but that's fine. I think we're still good on that. So that will be correct on this justification. Okay. And then part D. So the absolute sorry. Excuse me. At part C, the absolute maximum, that is, or minimum. Okay. Did I read that wrong? Oh my goodness. Absolute minimum then should have been f of negative 6. No, it should be f of 2. Okay, so this is the wrong one. I misread the problem. We're going to go back over that again then. F double prime of negative 5 and the f double prime of 3. So f double prime does exist at the negative 1 half. Yep, that's correct. Yep. So the f double prime of 5 does exist, and the f double prime of positive 3 does not exist because it has that corner on it. Okay, good. So we're good on that. Okay, onwards to problem number 4. Okay. So from what I have here is that starting at part A is that we have negative 16 and then the 91. That's good. That is correct. The equation and then the approximation of 43. That's also good. And then they want us to figure out that slope here of that negative 16. That was a cause for another point there. So all good. 4A is correct. Okay. The second derivative, so it's going to be an underestimate. That is correct. And with explanation, because we are going concave up because it is greater than 0. So that is good on the second part. And then with the third part, if we flip this over to part C, so this time, after a few runs, I finally got the integration down correctly. That we end up indeed with the g of t of 12 minus t over 3, all that cubed, and then plus 27 on the outside. This is indeed the correct response to that differential equation that we had, that they gave us. And then if we run through, it being 54, that is good on that too. Now, they actually did want to make sure that, so let's see, the separation of variables, which is exactly what we did here. We did separate out here, that's the cause for a point up there. Circle that, that's cause for another point. Running the antiderivatives, or running the integrals on this, so over here, again, that is a cause for another point. And then constant initial conditions, so again, we're having a constant plus c at the end, and running the actual work for The initial condition is good. Equation involving g and t, so rewriting it to here, the gt, that's good. And then the g of 3, which was there, that's good. So that's actually 5 points in which they are looking for inside of this problem. Now, it's a very, very harsh note, but I do agree 100%. You get 0 out of points if there's no separation of variables. So, what that means, of course, is that if you have not separated out the d of g to one side, so this step right here, by not separating out d of g and d of t, so that you can actually run the integral, I believe the test graders are concluding that you have no idea what you're doing and you deserve 0 points. I agree wholeheartedly with that. So that's quite something. Okay, so other than that, looks like that is all sorted out. I just need to go back to problem number 3 and to redo that segment again. Okay, problem number 3, the one segment that we were looking at here was going to be the absolute minimum question, because I wrote it down here as well myself that I am looking at an absolute minimum. Maybe smudging up my ink was not good because I wrote down absolute maximum as the answer, which is not correct. Okay, and so absolute minimum instead means that we won't be looking at f of -2. That's actually not correct. If it was a minimum, then we'll be looking at this point f of 2 instead. That'll be a different candidate as a minimum, because we're shifting from a negative side on the derivative graph, and shifting from negative to positive makes it a minimum on the original function. So let's go ahead and have a look here. So instead of f of -2, let's redo for f of +2. Now this guy though means that we're going to have to take the integral from -2 to +2 of the f prime of x graph. Okay, and of course that means that it's going to be, instead of f of 2, it's going to be f of 2 minus f of -2, and we just have to add it to the other side. Okay, so I'm running a little bit out of space here, but it should be fine because -2 to +2, that's literally just the semicircle, which we've already figured out before on the previous point. Let me double check where that was. This point here already. The -2 pi plus 3, that was already determined by our previous point. So -2 pi, that's the r squared. So this is already solved by us. So with that, -2 pi, and then we're going to add the 7 to it because we're adding f of -2. Again, that is going to be sent up there, and that will be f of +2 as a result. So again, this is going to be the 6.28 plus a +7, meaning that it goes to a 0.72 as an approximation of f of +2, which in comparison to the rest of our numbers here with the 3.72 and a +3 from f of 5 and f of -6 from our previous part A, f of 2 at the 0.72, now that is the absolute minimum as it should have been. So going back to the answers here, yeah, 7 minus 2 pi, that's correct. That's exactly what we did. So that is going to be the correct form of doing part C. All right. So a couple things I was a little bit careless on, but overall, looks like we're going for almost, still, I think we're right in the fringe of 90% on this exam. That was back in 2017 for AP Calculus AB. Pretty okay. Let's go on to problem number 5 and 6, and that really should be concluding it for our very first stream today. I'm glad to see that we're able to make it through here. Again, we're always open for new problems if anyone new comes in and requests for anything as such. So let's go ahead and have a look here. Going back, let's get to problem number 5. Okay, so we have two particles moving on the x-axis for 0 between t to 8. The position p of t is given by the function set xp of t. of the natural log of t squared minus 2t plus 10. Okay. Velocity is given of particle q is given by v of q of t is equal to t squared minus 8t plus 15. And then particle q, position of q, or I guess it would be x, xq at time is equal to 0 is equal to 5. So we're given an initial point for the q particle instead. Okay, that's all the context that they gave us. So they ask us the first question here, question A, for the interval from 0 t going all the way to 8. When is particle P moving to the left? Okay, good. So we have that question right there. So let's see how we can go about solving for it. P needs to move to the left, meaning that we need to know the velocity of the particle P respect to time. Of course, that's going to be the position function taking its derivative in respect to time. So that's pretty okay because we actually do have that equation in our hands, the natural log of t squared minus 2t plus 10, as was described by the question. And so we will just need to take its derivative in respect to time. Okay, pretty good. So let's have a look here. So by doing that, so we'll have the velocity of p of t. Running that through, we 1 over t squared minus 2t plus 10. Okay, and now we do multiply thanks to chain rule of 2t minus 2. So a little bit of both of the natural log derivative and the corresponding chain rule. Okay, so from there we will go about with the next part here is to understand then that if we can clear that up. Again, we want to know when it's greater than 0 because it must move to the left. Okay, so if it moves left, it would be less than 0. So if it's on the x-axis, yeah, moving to the left is going to be less than 0. So that's what we're looking for. Less than 0 shouldn't be too big of an issue, at least for this kind of problem. For our sense, though, is that for this particle, it looks like we have the following. So on the numerator, the 2t minus 2 is less than 0 only for negative t. Again, only for t is less than 0 as well. So that doesn't really work out for the numerator to ever have a negative value. So that's pretty nice. But the denominator, though, the t squared minus 2t plus 10, unfortunately here, though, it will also look like there really is no t would also be like some, yeah, there's no t, in which that denominator of t squared minus 2t plus 10 going through whichever numbers you wish, unfortunately will not give you any negative values either. So because of that, we can definitely conclude that particle P does not move to the left at the interval from 0 t to 8. Okay, I'll make that conclusion there. Okay, next up though is that then it's going to say for that same interval. Okay, find all times that the two particles travel in the same direction. Alright, very good. So for that part now, we can go about and figure this one out because again, the particle P is always to the right, thanks to what we have. Okay, then it's gonna be for us then to understand also, but also the v is equal to 0 at t is equal to 1 because of what we worked on so far. But then vq of t is equal to the t squared minus 8t plus 15, which in other cases we t minus 5 and t minus 3 factored. Of course, this is going to be useful because we have to do the number line analysis on this kind of equation that will again describe us how this guy is going to be moving. So we have the zeros for the velocity on this guy. Okay. Oh, the t's. I'm terribly sorry. Looks like I really messed up in problem A. Because at less than 1, doing our number line analysis for this guy at 1, again, it's going to be negative first and then positive afterwards. Okay, so it looks like particle P moves left at the time from 0 to 1. Okay, that is something that we will need to make sure to take note of for ourselves as this moves along. Then we go from 3 to 5 with the zeros for this kind of guy. So everything below that, so for example like a 1 that we can test between there. So we have both negatives, making it positive, and then we can test the 0.4 in between there, making it 1 negative, 1 positive, and then onwards like 6 as a test, both positive, so back to positive. So that is our number line analysis for the velocity of q. And again, our velocity of p, that's q, p is going to be 1 there, and it was negative to positive from that. Okay, so because of that, they will move together in the same directions from 1 to 3 because they're both positive, and then from there 3 to 5 are all out, and then it's going to be 5 to 8 will also be both positive. Thanks to our number line analysis, they will both move in the positive direction at 2 different time segments there. Okay, pretty good. So let's go onwards to part C. Find the acceleration of particle Q at time is equal to 2, and then is the speed increasing or decreasing at t is equal to 2, and we must explain the reasoning behind that. Okay, very interesting. So we need to know a speed equation based off the acceleration. So we can do that first. The acceleration of q is fine. Speed, of course, is a little bit of an extra analysis of what the acceleration and velocity have together. But nonetheless though, the acceleration of q respect to time, that's going to be the velocity derivative of q respect to time. So if we take the velocity of q, let's see, that was going to be described as, if I can find that, there you go, the t squared minus 8t plus 15. Take that derivative, so that's going to be 2t minus 8. Okay, and a little bit of a number line analysis on this really quickly is that at the point of 4, everything below that's negative, everything after that is positive. Alright, pretty nice. That's good. Why is that important? Of course, remember that speed is a relationship between, speed compares velocity and acceleration. Okay, so idea being that if they're both positive or if they're both negative, again, those are both speed ups, because speed does not care for your direction. So in that case, you're just really caring if they're the same or if they're different signs. So positive, negative, negative, or positive for velocity and acceleration. Those are slow downs. Okay, that's again still why the number line analysis is important, because they want us to also then determine that t is equal to 2, so v of 2 for particle q, at least just looking at the sign itself, that's a positive, but the acceleration of q at time of 2 is a negative value. Again, that number line analysis really coming in clutch for us, because with those having different values for the speed, that different values for acceleration velocity, that is going to be a slow down. Thanks to what we've deciphered from looking at both the acceleration and the velocity of this kind of particle. Okay, let's go to the last part, D then. Find the position particle Q. For the first time it changes direction. Okay, so change in direction, huh? Change direction of Q first time, and it's T. Okay, so change direction, well, that's going to be a velocity question for T, and thankfully we could just copy and paste the exact number line analysis, because a velocity change for direction wise is going to be the sign change on the number, and that will be right there already. At time is equal to 3, the velocity shifting from positive down to negative. Okay, so at time is equal to 3, the direction changes for particle Q. Very good. Thankfully, it's our work that we've already done before that really does put everything back into perspective. Very nice. So let's go to our final problem 6, and then we'll correct, and that should really conclude it for today's first stream. I'd say it's quite successful, at least for what I could offer. Hopefully, if we can garner some more attention on this, we should be able to start answering some real-life questions from actual students. But for now, if all I need to do is keep doing these types of free response questions, I don't see a problem on it either way. It's a good place if it's going to be in a VOD for people to view later on. So, nonetheless, though, we have question 6 here. I got quite a few things I need to start recording down. We have a table of x, g of x, if I don't make sure I run out of paper space here, g of x and g prime of x, these three guys. So on a table, we have x going from -5, -4, -3, -2, -1, and a 0. And g is ordered from 10, 5, 2, 3, 5, 2, 3, 1, and 0. And then g prime is -3, -1, 4, +1, +2, -2, -3. There you go, like that. Okay? And then we get a graph associated with that. This is a graph of h. Okay? So, looks like we go across 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, so we have 5, 1. Should get all of our tick marks here. 5, 1. Then it's going to be -5, 4, 3. -3, +2. It keeps like that for 1 point. Goes to 0. Graph this part first. Like this. And then from 3, -1. Like that, and then going all the way to 3, 4, 5 to looks like 5, 3. A couple more. Okay, there you go. We have the graph of h. Not the worst thing in the world. We can refer to that at a later time. So now we got more context here. So f defined f of x is equal to cosine of 2x plus e raised to the sine x power, and then g is differentiable. Okay, and then we have that on table already. Okay, and then h is already shown as that. Okay, we have a lot of functions here. We have g, f, and h. Quite a few things, and we got our questions coming in then. Okay, so find the slope of the line. Let's see, tangent to the graph. Tangent to the graph of f at x is equal to pi. Okay, this one's pretty straightforward. We're dealing with the slope line for f at a specific point. Pretty easy. We're looking for pi f prime of pi. So we need to find first f prime of x. Let's go ahead and take the derivative of x, which is the cosine of 2x plus e raised to the sine of x. Hopefully that shows properly that that's an e in there. Okay. So the derivative there is negative 2 times the sine of 2x, keeping track of both chain rule and the cosine rule of derivatives. And then next up we have a positive cosine of x times e raised to the sine of x, once more keeping track of the chain rule and the exponential rule for this type of function. So by going f prime of pi, we can then go ahead and plug in. So it's negative 2 times sine of 2 pi plus cosine of pi e raised to the sine of pi. Got a lot of stuff going on in there, but if our camera can focus, we shouldn't have too big of an issue with the stuff that is going on in here. Come on, camera. Alright. Why do you mind keeping it like that for a little bit longer? So, sine of 2 pi, this guy already goes to 0. That's nice. Cosine of pi, that goes to a negative 1. E raised to the sine of pi, that's 0. So, with some easy trig related identities here, we get 0 plus all of negative 1 times e raised to the 0 power. That's what our first line simplifies to. Then that's going to be a negative 1 times a positive 1, which is just negative 1. That is quite the easy slope to deal with from this kind of problem. Very nice. Let's go onwards to part B. Because again, this is just the slope. We're not looking for anything else, not the equation, just the slope, and we did just that. So then they'll tell us here that let k be the function defined by k of x is equal to h of f of x. So find k prime of x. Okay, so we got a lovely chain rule coming on here already immediately, with k prime of x being described as h prime of f of x and then multiplied by the f prime of x. Okay, so why don't we first discover here, okay, what the h prime of f of x looks like. So we have here, we have the h prime of f of x. So h of f of x first. Okay. This guy will result in, let's see here. H was already there. Okay, yeah. So because of this, we're going to do, because h is only given by the graph, right? Yeah. Okay. I want to make sure we're on the right track here. So, oh, it's not a x, it's a pi, that's why. Oh, geez, okay. There you go, okay. That makes a lot more sense. I was going to have a moment there. Got to make sure we read the problem. So again, that's k prime of pi. So they actually gave us a point to find on that derivative. Always reading the problem is very important. So h prime of f of pi times f prime of pi. Okay. F prime of pi, thankfully, we've already figured out earlier. That is negative 1. Pretty nice. And then f of pi, though. Now that's going to be a little bit different. So we need to find that first. F of pi is equal to, if we go about that, let's see, it's going to be cosine of 2 pi plus e raised to the sine of pi. Okay. So again, sine of pi up there on the exponent 0. Cosine of 2 pi this time is a positive 1. Equal to 1 plus e raised to the 0, which is equal to positive 2. That's good. So then next is going to be h prime of a positive 2 times a negative 1. H prime of 2, that means we're going to have to refer back up to the graph. 2 is going to be this point there on that negative line there. So again, this is this line part there, so the h prime of 2, that guy. If I can make sure that we swap over to something better here, like that. Okay. All right. So we have h prime of 2. This is going to give us the slope function that we need to take of -1 minus 0. Let's see, and x2, which is a positive 3 minus 0. -1/3 is determined from the points 3 comma -1 and then 0 comma 0 for that line segment right there. So that's where h of 2 was. So then we need to go and figure out where that derivative will lie. So with a -1/3 times a -1, connecting that there, that's k prime of pi is now equal to a positive 1/3. Very good. A few steps that needed to be taken there for us to be able to determine what, with a little bit of chain rule, what that turns into. But it didn't turn out too bad for us. Onwards to part C. So m is a function is equal to g of -2x times h of x. And now we want to find m prime of 2. A little bit more chain rule stuff going on here, but nothing we can't really be able to handle. M prime of x, by going at it through there, is going to be g prime of -2x multiplied by -2 times h of x. And now, because those are two functions multiplied together, we're going to need to do some product rule. So I'm going to add that with g of -2x times h prime of x. There you go. Some simple derivative rules to help us understand how to go about this problem. Okay, so next up though, we're going to have to go plug in for positive 2. So g prime of -4 times a whole -2 times h of 2 plus g of -4 times h prime of 4. There you go. Not bad at all. So it looks like we have just a few things to go about here, and then we should be well on our way. So g prime of -4, that already is defined with us on the table. Back at -4, that's going to be a -1 up there on the table at the very top. So that's -1. The -2 stays, that's going to multiply later. H of 2, oh, we already have that back there. H of 2, though, is going to be a little bit different here because 2 is not exactly on the graph. 2 is going to be a -2/3, so that's 2/3 step of the way they're getting to -1 on the H graph. And they're going to add that with g of -4, which g of -4 was given to us on the table there, right, as you can see. So it's positive 5. And h prime of 4. Let me double check here. Why did it show 4? It should be h prime of 2, not 4. H prime of 2 we already figured out before, which was -1/3. Okay. Good. So we have everything we need here to solve for that. So that's going to be a -4/3, and then we're subtracting a 5/3 after the fact. So -9/3 from a little bit of work. -3 is the result of m prime of 2. Okay. A few extra steps needed here. Kind of smudged it, unfortunately. Got to work on making sure the ink dries first before I put my hands on there. But nonetheless, that should be part C. The very last part here is part D, and we can get to checking. So, they're asking, is there a number C on the closed interval -5, -3 in that closed interval such that g prime of C is equal to -4. Okay, so they're asking about that. Okay, g prime of -4, well, that's going to be g prime of C is equal to -4, yeah. Okay, so let's have a look here, right? This guy right here, if we're gonna look, right, we want a specific number on the derivative from the interval. Oh dear, that looks exactly like mean value theorem, if you remember what that is, right? Okay, thankfully though, they've already told us that g is differentiable on the table, and right, so that seems to be pretty okay. So how then can we get a match of -4 as part of the slope? Well, for one, right, are there any points in which we can be able to reach that negative 4 slope. Let's have a look here. The actual average, the change here, so again, this is going to be the points -5, comma 10, and then let's see, from -3, so -3, comma 2. So we have those 2 points here at the two parts that they asked us for inside of this function of g. So let's go and find that slope to determine what the average rate of change is going to be. So y2 minus y1 over x2 minus x1. That's a -8 over a +2, and that is exactly equal to -4. And maybe I want to redo this part here. So it's 2 minus 10 over -3 minus -5, and -8 over 2. So with that line of work, this does match that the average rate of change that we're looking for does match the g prime of c, which is equal to -4. Right? Now they're not asking us for the exact number, they're asking us if there's an exact number, and the answer is going to be yes, according to mean value theorem that we just used right now. We've measured the average rate of change, the slope just between the endpoints of our interval. We figured that one out, what the classic y2, y1, x2, x1, and so we did match that the average rate of change does match exactly the derivative that they're looking for. Pretty good. All right, so those concludes those 2 problems. So we can go back and check them, problems 5 and 6, and that will really conclude for today, finishing the entire packet of the 2017 AP Calculus AB free response question section. So let's make sure we got this. We got problem number 5 here that we went over with my correcting pen this time. So part A, going back to it, is that we have the particle P moving left from only 0 to 1. That's good. That interval is indeed correct. And again, they want us to make sure that we did find v prime, no, not v prime, x of p, take that derivative that was stated there by taking the derivative into this, the new velocity, times the chain rule. That is going to be a cause for the second point. Good on that. Part B says that if we're going to have they move in the same direction from 1 to 3 and then 5 to 8. So we have both intervals, so we're good on that point. And the analysis using the number line, they also use exactly the number line analysis on this kind of problem. That will be the cause for the next point. Going to part C, we have the comparison between the acceleration being a negative number, so we're good on that. Velocity being a positive number. Again, so because we made that description there of a of 2 versus v of 2, we then conclude that it's slowed down, so that is correct. So you did everything we needed to in part C. Lastly, part D is that we end up with the t is equal to 3, change direction, so that's good. That's exactly what we wanted, right? We need to take the antiderivative, so we needed to go and take the, I guess we kind of didn't have to. I wonder what they're going on about, because we really just needed to just take the change in direction. Is there something else that I'm not getting at here? Oh, find the position. Oh, geez. Well, looks like we have something to go back on, because we actually did that wrong. We got the first part, so I guess I only really get 1/3 of the answer there. I needed to read properly that it has to be the full position and not just the exact time. We'll get back to that. Okay. So, no, that's the wrong side. Let's go flip this back over to question number 6. Okay. So, we have then the actual f prime of pi, and that does result in -1, so that's all they really want to care about right now. The work all checks out. Okay. Then part B is that we want k prime of x to show so that's first cause of a point right there of actually understanding what chain rule looks like, and then resulting in a positive 1/3. for k prime of pi. That is also correct. And then lastly, not lastly though, actually we still have 2 more parts to go. So part C, by running m prime of x, so we'd still run this. So this entire thing of how we implemented both the product rule and the chain rule to make a proper derivative is the first cos for a point. Second cos for a point with the -3 coming off of m prime of 2. So that's good. That's correct. And let's see, part D is that because we ran, yes, they cared a lot about that slope form of finding the average rate of change that was needed for the mean value theorem. They exactly wanted us to talk about mean value theorem to make our case right there. So that is also correct. So the entirety of part 6 looks like I got correct. But let's go back to problem number 5 to go back to that one part that I missed because I didn't read properly. Okay. So it's not find the time, but we need to find the position of the particle Q. So that is a little bit of an oversight on my side. We had to go back to that. So we understood at least the work there is still partly what we needed, because at time e is equal to 3, we need to find the x of q of t. Okay, and the only way to be able to do that is that we need to go take its integral. Right now we can range that because they give us the initial points of 0 to 3 that we figured out of our velocities of v of q of t dt. Okay, so if we were to move this over, the integral is 0 to 3 v q of t dt, so that velocity graph of the particle, that in itself will give us the first 2 points. So the position at time is equal to 3 minus the position at time is equal to 0 of particle q. Now this we've already understood as something that they gave us at the very start of the problem. X of q of 0 is equal to 5. Again, this they already gave to us. So by doing that, we can lock that down as 5. And now this we actually have to run the integral for. Right, so the integral from 0 to 3, that does show right there, yeah, integral from 0 to 3 for the velocity of q, which they've already given us as t squared minus 8t plus 15. This is equal to 1/3 t to third power minus 4t squared plus 15t. Again, this is a definite integral of an equation, so we need to run the analysis from 0 to 3. Thankfully at 3, that's pretty simple. We just plug in 27 minus 4 of 9 plus 15 times 3. Now, of course, with everything having a variable at the end of that, the second half just goes to 0. So we can run these last calculations. 9 minus 36 plus 45. So by doing that, this will then be another positive 9, so it's positive 18 on that side. So we have positive 18, which is equal to x of q of 3, that position that we are looking for, minus a 5. Adding 5s to both sides, we get 23 is equal to x sub q of 3. That is the position at time is equal to t, time is equal to 3 for that particle. So again, this is a 2-part problem, at least for us, is that we found the time in which it changed direction. So this was all still good. That's still all fine. That we did the number line evaluation, but then we actually had to run the integral such that we can figure out the exact position at an exact time for this function. And that 23 was exactly what we needed for us to get full points on part D. Okay, 6 problems and 6 pages. Who would have thought? We got 1, 2, partly for problem 4. So 3, 4 on that, 5, and then 6 with problem 1. So we got all 6 problems done. I wonder if I can actually grade that part. Do they have that? Do they have the grade numbers here? If I really were to go about it, the scoring guide. Is this the scoring guideline? Is just the actual. No. Let me double check. Is there statistics and distribution? I wonder if this works here. Okay. Let's see here. Okay. So mean score of 2.93, standard deviation of 1.4. So if the mean was meant to be basically two standard deviations higher, let me double check that. 2.93, and then going for 3, 4, 5, 2.8, 5.63. I don't know. Oh, that's just a score. Well, in any case, though, I think we'll have to go look at that a bit deeper. This is not just as easy as the SAT, I would say. But in any case, though, I think that will really conclude it for today. Hopefully this VOD will most likely be saved on the main LabCoat Math channel. Yeah, so with this, just as a reminder that we will be doing this hopefully twice a week, going through a full section. If things continue to be a bit slow, we'll be going through a full section of the AP Calculus FRQ problems, and then we'll be able to get onwards to some other ones by request, hopefully in the future. So thank you everyone for watching here today. This really was quite the blast to go through, while putting myself under a lot of scrutiny over these problems. But nonetheless though, that really will end it for today, and we'll see you within the next couple of days.